in the previous lecture we have seen that your normalized one, that is just a 2 into 2 matrix, right, and this is your what you call that normalize your participation factor, right. So, the ith column entities in the P or P normalized matrix are the sensitivities of the ith eigenvalue with respect to the states. This is the previously we have seen some example, but I again took a couple of example just to demonstrate certain things, right. Now, next another example is taken. So, compute the participation factors corresponding to the complex eigenvalues of, right. A is equal to, this is my A matrix, it is a 3 into 3 matrix. So, minus 0.40, this is 0, this is minus 0.01, this is 1 0 0 and this is minus 1.4, 9.8 and minus 0.02, right. Now, when you find the eigenvalues of this matrix, so one eigenvalue is real, that is minus 0.6565 and other two are complex conjugate pairs, that is lambda 2 and lambda 3 are 0.1183 plus minus j 0.3678. So, these three are the eigenvalues, right. Here the right and left eigenvectors corresponding to the complex eigenvalues you find out, right. So, only corresponding to this you find out the right and left eigenvectors, right. Earlier how to find out right and left eigenvector, that everything has been shown. Similar way you proceed, right. Here I am just giving you the answer. Similar way you proceed, you will get this is my right eigenvector. So, it is your and this 2 stands for, this is eigenvalue lambda 2, that is 0.1183 plus j 0.3678, that is why it is written V 2, right eigenvector. This is for lambda 2, it is 0.0138 minus j 0.0075, this is minus 0.0075 minus j 0.04 and this is minus 0.9918 minus j 0.12 G3, right 03, right. So, this is right eigenvector. Similarly, left eigenvector corresponding to the same eigenvalue lambda 2, it is 0.835 minus j 0.0577, this is 0.4469 plus j 0.307 and this is minus 0.0061 plus j 0.0205. This you know how to find out, right. So, just you find out that your basically your what you call, you can find out that your V matrix, a phi matrix and psi matrix, here also V matrix and W matrix, the way you have obtained previously, same way you follow, right. So, now using the formula in the previous section, you can obtain that P using the previous formula means this one, right. I will go back to this, right, this one, this formula, that is equation 52, right. So, follow the same thing, equation 52, right, and then you come back to this. So, if you follow this, that equation 52, you will get that P21 will be 0.2332, P22 0.3869 and P23 0.3772, right. So, note that P21 because it is normalized. So, P21 plus P22 plus P23 is equal to 1. So, we can normalize with respect to P22, right, making it unity in which it can be, I mean highest is your what you call that your P22 is 0.3896. So, divide everything by 0.3896. So, in that case P22 normalized will be 1 and if you divide by P22 values all are P21 and P23, it will be P21 normalized will be 0.598 and P23 normalized will be 0.968, right. This way one can find out. But in this case one thing you have noticed that your it is there is no your what you call as it is your what you call that magnitude is considered, right, and it is normalized and you will see that no angle is appearing here, right, only magnitude. So, after this we will go to some general thing. Now, whatever we have seen so far, that regarding your dynamics basically it is a dynamics and control of your what you call small signal stability analysis for synchronous machine. So, only we have restricted to that which is possible for your classroom exercise, right. So, that is why simulation other things generally I have tried my best to avoid those things, right. So, now characteristic of small signal stability problems. Now, in large power systems small signal stability problems may be either local or global in nature. Some general ideas, right. Now, local problems. Now, local problem involves a small part of the system, right. They may be associated with rotor angle oscillations of a single generator or a single plant against the rest of the power system, right. Such oscillations are called local plant mode oscillations. So, certain terminology you should keep it in your mind. So, that this is called local plant mode oscillations, right. Now, next is the stability problems related to such oscillations are similar to those of a single machine infinite bus system. Most commonly encountered your small signal stability problems are of this category, right. Local problems may also be associated with oscillations between the rotors of few generators close to each other. Such oscillations are called intermachine or interplant mode oscillations. This terminology you should keep it in your mind, because this is underlined also, right. Usually the local plant mode and interplant mode oscillations have frequencies in the range of 0.7 to 2.0 Hertz, right. Other possible local problems include instability of modes associated with controls of equipment such as generator excitation systems, HVDC converters and static var compensator, right, that is SVC. The problem associated with control modes are due to inadequate tuning of the control system. The parameters has to be optimized or proper tuning is necessary, the control parameters. In addition, right, these controls may interact with the dynamics of the turbine generator shaft system, causing instability of torsional mode oscillations. This one, this torsional mode oscillations, I thought I will cover little bit, but later I decided I should skip it. By chance if I get some time at the end, we will see that, right. It will take few equations and how it is done. So, this is actually instability of torsional mode oscillations, right. Analysis of local small signal stability power systems require a detailed representation of a small portion of the complete interconnected power system, right. The rest of the system representation may be appropriately simplified by use of simple modes and system equivalent, simple models and your system equivalents, right. Usually the complete system may be adequately represented by a model having several hundred states and states at more. I mean, if you can consider that interconnected system, so many machines are there, so you will have several hundreds of states variable, right. Another thing is the global problems. Global small signal stability problems are caused by interaction among large groups of generators and have widespread effects, right. They involve oscillations of a group of generators in one area swinging against a group of generators in another area, right. This is actually this kind of stability problem, that is multi machine system, right. So, it is beyond the scope of this course actually as far as classroom exercise is concerned, right. Such oscillations are called inter area mode oscillations. Large interconnected system usually have two distinct forms of inter area oscillations. First one is a very low frequency mode involving all the generators in the system, right. So, system is essentially split into two parts with generators in one part swinging against machine in the other part, right. That means a group of generators say swinging together, swinging against that your what you call group of machines in another area, something like this, right. The frequency of this mode of oscillation is on the order of 0.1 to 0.3 Hertz, right. Second one is that higher frequency modes involving subgroups of generators swinging against each other. The frequency of the your frequency of these oscillations is typically in the range of 0.4 to 0.7 Hertz, right. So, with this, that your synchronous machine part with all this, it is almost over. Only thing is that if time permits, I will see little bit of excitation system of synchronous machine, that is if time permits, right. Now, next what we will do after this, we will move to the transient stability analysis, particularly for multi machine system, right. Next one will be that your transient stability analysis for multi machine system. So, here I forgot to write that headline, it is transient stability analysis. Transient stability analysis, right. So, basically your in power system analysis course, there single machine infinite bus we have seen it, right. So, here we will see that multi machine system, but let me tell you one thing, at the at your what you call that your simulation another thing, right, and those techniques we will skip, because in the classroom we cannot do that, right. So, only I will think from the point of view of classroom exercise. So, in the case of this transient stability analysis, this first we have to see the classical model of a multi machine system. So, number 1, mechanical power input, we assume that it is a constant, we have to make some assumption. Number 2, damping or asynchronous power is negligible, right. So, based on certain assumptions we will move. Number 3, constant voltage behind transient reactance model for the synchronous machine is valid, right. Number 4, the mechanical rotor angle of a machine coincides with the angle of the voltage behind the transient reactance. Number 5, loads are represented by passive impedances or admittances, right. Here admittance is not written, either passive impedances or admittances. This model is useful for stability analysis, but is limited to the study of transients for only the first swing or for periods on the order of 1 second, right, maximum. Now, assumption 2 is this one, that damping or asynchronous power is negligible, right. So, assumption 2 is improved upon somewhat by assuming a linear damping characteristic. A damping torque or power, the d omega that we have seen previously, right, is frequently added to the inertial torque or power in the swing equation. The damping coefficient d includes the various damping torque components, both mechanical and electrical, right. Values of the damping coefficient usually used in stability studies are in the range of 1 to 3 per unit, right. This represents turbine damping, generator electrical damping and the damping effect of electrical loads, right. So, this is the range of that value of that your damping coefficient in between 1 to 3 per unit, right. Now, assumption 5 is this one, that loads are represented by passive impedances, right, or admittances. So, assumption 5 suggesting load representation by a constant impedance is made for convenience in many classical studies, right. Loads have their own dynamic behavior, which is usually not precisely known and varies from constant impedance to constant power, right. So, we will take here that constant impedance, right. So, now constant impedance is an inadequate representation. Load representation can have a marked effect on stability results, right. So, this figure little bit faint, right. So, I am bringing a good figure, just hold on, right. So, same page, I mean just I have redrawn this. So, constant impedance is an inadequate representation. Load representation can have a mark your what you call on stability result. Now suppose you have a machine system, right, and this is my transmission network, right. So, generators are there. Suppose you have n number of generators, right. So, voltage behind this transient reactance, that is given E 1 angle delta 1, then E 2 angle delta 2 up to n, right, up to n E n angle delta n. Then the impedance here is given R 1 plus j x d 1 dash, R 2 plus j x 2 dash up to R n plus j x d n dash, but usually that R 1, R 2, R n this is negligible. So, in our studies we will only consider this x d dash in general, right, x d 1 dash, x 2 dash, x d n dash, and this E 1, E 2 your what you call this your this up to E n, right. So, these are actually generator voltage behind your transient reactance, that is E 1 angle delta 1, E 2 angle delta 2, like this, and these are the bus bars. Say for example, say this is bus voltage V 1, V 2, like this, or maybe any bus number. These are the buses, right. So, this and this dash line, this is basically a reference node or common node, right, that I will move later. So, and this side that you have a load, you have constant impedance loss, you have r number of buses, right. So, it is say current here is IL1, here it next one will be IL2, ultimately it will come to ILR, right, and this is my transmission network, and this is my your all the generators, in number of generators, and there you have r number of your load buses, right, and this is node 0, actually we call it is a reference node, right, and this actually figure 1 it was representation of a multi machine system classical model. So, this way we can represent your what you call that n machine system, right. So, this is shown, actually this figure was faint, that is why I showed the other one. Now, node 0 actually is the reference node, that is neutral, right. So, nodes 1 to n I told you are the internal machine buses, right, or the buses to which the voltages behind transient reactances are applied, right. So, passive impedances connect the various nodes and connect the nodes to the reference at load buses, right. So, initial values of E1 tilde, E2 tilde up to En tilde are determined from the pre-transient conditions, right. Thus, a load flow study for pre-transient condition is needed, right. So, this figure is original actually better figure I shown. So, I have shown you. So, this voltage is E1 delta 1, this is E2 delta 2, right. So, once load flow is known, then E1, E2, En and delta 1, delta 2 up to delta n all can be computed, that we will see later, right, and the current flowing here is I1, I2 up to In, right, and these are the internal your what you call that these are the, this is marked actually, this is internal one, right, this is 1, this is 2 internal machine buses up to this n, right. So, let me clear it. So, initial values of E1 tilde, E2 tilde up to En tilde, these are phasor quantities, that is why tilde I have used, are determined from the pre-transient your what you call condition. Thus, a load flow study for pre-transient condition is needed. Now, the magnitude of EI for I is equal to 1 to n are held constant during the transient in classical stability studies. Once that E1, E2 up to Ens are computed, then it will remain constant, right, during transient. This is an assumption. The passive electrical network described above has n nodes with active sources, right. The admittance matrix of the n port network looking into the network from the terminals of the generator is defined by, I mean we know that I is equal to YV and here it is E. So, your generator terminal voltage. So, I tilde is equal to Y tilde E tilde, right. This is not for you, this is for my own reference, right. So, by definition that YII tilde from load flow studies you know it is YII angle theta II. Theta YII means this is the magnitude, right, and theta I is the angle, and this is called driving point admittance for node I. This already you know from the load flow studies is equal to, we can write GII plus JBII and YIJ tilde is equal to YIJ angle theta ij. So, YIJ is the magnitude and theta is its angle, it is negative of the transfer admittance between nodes I and J. This also you know from your load flow studies, right. So, this is equation 1 and this is nothing, this is for my own reference. So, next one is that so YIJ also we can write that GIJ plus JBIJ, this is equation 2, right. Now, the power into the network at node I, which is the electrical power output of the machine I, is given by that PEI we can write real of EI tilde into II conjugate tilde, this is real part of this one. If you make real from your load flow studies you know how to do this, right. So, we can write PEI is equal to EI square GII plus sigma J is equal to 1 to n, J not is equal to I, EI EJ YIJ cosine theta ij minus delta I plus delta j. That from your load flow studies you know when you have taken ith term out from this one it is EI square GII. That is why here it is written J naught is equal to, you have load flow studies also you know Pi is equal to J is equal to 1 to n, your Vi, Vj, Yij cosine theta ij minus delta I plus delta j, this way right now. So, this equation when you write like this say j is equal to 1 to n, right, then you can write ei, then you can write ej, then you can write yij, then you can write cosine theta ij minus delta I plus delta j. This is you know for you from for the your what we call load flow studies. Now from this expression, when you are taking your ith term out, right, that when suppose j is equal, I mean when j is equal to say 1 2 this way, 2 3 this way, one I will come, then it will come to n, right. So when ith term is out from this sigma, so it will be when j is equal to I, so it will be basically your what will happen, that it will be your ei into ei square, it is yii, and this I is equal to j means this term will vanish, it will be theta yii cos theta ii. So basically ei square gii, that is why it is written like this, right. So that is why that pi is equal to ei square gii, j is equal to 1 to n, j naught is equal to I, right. Your what you call ei ij yij cosine theta ij minus delta I plus delta j for I is equal to 1 to n, right. Next is that pi, I mean this term you can I mean before going to that, right, this term, this cosine your theta ij minus delta I minus delta j, right, this one we can write no, cosine theta ij cos a cos b plus sin a sin b. So cos delta I minus delta j, right, plus your sin theta ij, then sin delta I minus delta j, right, this term. So that is what we have done here. This one we can write, then ei ij bij sin delta I minus delta j plus gij cosine delta I minus delta j, right. I mean if you when you are expressing this one, so this is say yij, and this term just I wrote no, cosine theta ij cosine delta I minus delta j plus sin theta ij, then sin delta I minus delta j, right. So that yij cos theta ij, it will be your gij into cos delta I minus delta j, and this one yij into sin theta ij, so bij sin delta I minus delta j, or this term we have written first. So bij sin delta I minus delta j plus gij cosine delta I minus delta j, right, that this term we have written there. So that is why this we are writing that ei square gii plus j is equal to 1 to n ei ij, it is bij sin delta I minus delta j plus gij cos delta I minus delta j. I showed you that this is the thing, and this is also for I is equal to 1 to n, this is equation 3, right. Now the equation of motion are then given by these swing equations we have seen before for synchronous machine analysis. So this same thing we can write 2hi upon wr, right, over rather omega r, that is a reference speed, right, into d omega I dt plus di, the damping term, damping coefficient omega I, is equal to in general Pm minus P, but Pmi minus Pi, this is for ith machine, right, and that means that 2hi upon omega r into d omega I upon dt plus di omega is equal to Pmi, and this Pi, Pei, this is the expression for Pei, you substitute here, there is minus in bracket ei square gii plus j is equal to 1 to n, j not is equal to I, ei ij yij cos cosine theta ij minus delta I plus delta j, right. This is your equation for omega. Another thing is di upon d delta I upon dt, this also we have seen that omega I minus omega is the reference speed and omega is the speed for the ith machine, omega I minus omega, this is for I is equal to 1 to n. Actually these two equations are equation 4, right, this is nothing. these two equations actually equation 4 together, right. I have written here is 4 is here, basically these two equation together it is equation 4, right. So, it should be noted that prior to the disturbance at t is equal to your 0 minus, I mean just before disturbance, PMI 0 is equal to PI 0, actually it was balanced, right. PMI 0 mechanical power input is equal to electrical power output, PI 0, right. So, that means just before disturbance PMI 0 is equal to, then we can write same equation, but using one suffix 0, that EI square GII 0 plus sigma j is equal to 1 to n, j naught is equal to I, EI ej y I j 0 cosine theta I j 0 minus delta I 0 plus delta j 0. This is equation 5, right. So, this is nothing, that it is actually before disturbance, right. Before disturbance this thing you will get it, because once your what you call load flow studies are carried out, later we will see when I will take the example, that from that load flow studies your voltages, the internal machine bus voltages E1, E2, E3 up to E and all will become computed, right. All the angles will be known. So, at that time you can easily find out what is your PI 0, and PI 0 is equal to nothing but by your PMI 0, right. So, thank you very much, we will be back again.